Hey everybody, welcome back to round 2, electrical requirements. In this video, we'll be going from a basic layout that only really dealt with the physical constraints such as space, clearance about devices and equipment, and orientation and tilt considerations, to looking at how the electrical characteristics of the proposed array need to be compatible with the selected inverters given environmental conditions for the site. We will, however, be glossing over the other critical aspect, which is how the PV system needs to be interconnected to the building's distribution system. For the purposes of this exercise at this time, we'll just be assuming that the equipment is going to connect at 480 volts, 3-phase to the distribution system of the building, and that it's really just a non-issue. Now, I filmed my process with the best intentions, pretending to know exactly what I was doing and assuming everything would work out according to my preconceived expectations. It didn't. I decided to leave almost all of that in as it's part of the process. And furthermore, it once again emphasizes the importance of needing to understand the basics of PV system design and the constraints involved, because in the end, we got a really clean system that has a consistent design that's going to pay dividends over the life of the system. Finally, I also realized pretty early on that the template drawings that I was working with in PDF form didn't fit. They just weren't a good fit. And I tried to make some efforts as I was going to force this system into that box, but it really doesn't go. So I think I'll probably make another video where I use CAD software as opposed to trying to manipulate the PDF in order to illustrate how to get the system we end up designing clearly organized and described in an efficient single page, single line diagram. So with that being said, let's get into it. Alrighty, picking up from where we last left off. In the first section, we established the theoretical physical maximum number of modules that could fit on this roof. And that's all fine and good, but it doesn't necessarily mean we have a constructible system just yet. So we looked at how many modules we could fit based on physical constraints. So we took care of the offset for access around the perimeter. We also looked at setbacks from equipment for working clearances, as well as roof access hatches. And then we also looked at inner row shading. We were using the 10-degree racking system for our first iteration, if you will. And this established the number of panels that we can fit on the roof given the physical constraints. However, this doesn't necessarily mean that this system is constructible, because it doesn't really look at any of the electrical characteristics of the equipment. So if we just wanted to get a rough idea of how many modules are on this roof and what the equivalent DC power rating is, all we would need to do is figure out how many fit. So if we click on the module, go to entity info, we know we have 468 of them. Let's do a quick little math here. 468 times, we were modeling this off of the 365 watt modules. That means we've got 1,666,608 watts, or 166.6 kilowatts. Now, 468, is that divisible by the number of modules we're going to have in a string? Is that divisible by 20? Nope. 468, 19. Nope. 468, 18. 18's looking pretty good. We'll see how that lines up later. What about 468 divided by 17? 468 divided by 17, 27.5. So that's a fractional module. We can't do anything with fractional modules. So how do we go about looking at the electrical characteristics of this system such that the modules work within the physical space and also work with the electrical components. So let's take a look at the modules. We have the LG Neon 72s, and we are looking at the 365 watt modules. Just put a little box around that so we can focus on that as we move forward. And we're also working with the Yaskawa PVI 23 TLs, 28 and 36 TLs. For argument's sake, just to get started, let's constrain our exercise to the 28 TL. Doesn't really matter. We could have picked any one of these. And as we go through our future iterations, we may select the 23s, maybe the 36s, or maybe even a combination of all three. Don't know yet. That's kind of the fun part of the exercise. One of the first things we need to look at is concerning ourselves with the voltage of the system and how many panels we can put in series. If we were to look at this system, these three dots means there's any number of panels between these two and the last one in the string. It's just an abbreviated way of showing multiple modules in series without having to draw out every single module. So we could have 3 modules in a string, 4, 5, 20, doesn't really matter. But it needs to fit within the electrical constraints, both from a safety standpoint with the National Electrical Code, as well as an operational standpoint based on the equipment selected. How do we do that? Well, the first thing we're going to look at is open circuit voltage. So how do we figure out what that looks like for this system? Well, let us look at the cut sheet or the spec sheet of the modules. And here we have the 365 watt modules, and these are at STC, so standard test conditions. At STC, the open circuit voltage for this panel is 48.4 volts. We can see that right here. Now, 48.4 volts is under STC. And if we zoom in, STC for this module and almost all modules, sorry about the plane flying by, hope it's not too loud. Standard test conditions for this module is 1000 watts per meter squared irradiance with a module temperature of 25 degrees Celsius. We don't need to concern ourselves with atmosphere. So we know the standard temperature is 25 degrees at 1000 watts per meter squared irradiance. Under those test conditions, you've got 48.4 volts. So if we were to say, bring this back up and we zoom in, let's add some text. So if this module is 48.4 volts, this one is 48.4, this one is 48.4, then we know our string, I'm in caps lock, our string voltage open circuit equals 48.4 volts times the number, let's just go number mods in series. In other words, 48.4 times, let's say we had, let's call it 10 for round math. Oop, clicked off, 10. So we know that equals, just move the decimal point, 484 volts open circuit. That's if we had 10 modules in series. Now, how many modules can we put in series? Well, to figure that out, we need to look at our inverter. So our inverter says the absolute maximum input voltage is 1000 volts. Good to know. The other important piece of information is what's the operating voltage range, 240 to 950, and what is the maximum power input voltage range, 500 to 800. Well, let's start with the absolute maximum input voltage of 1000 volts DC. So we could calculate this, pen and paper. We could also input it into one of the many voltage against temperature coefficient formulas that exists, but I'm not really into memorizing formulas per se. I would rather just understand what needs to happen and then run the calculation. The formula will then derive itself as you work through the maths. So let's open up Excel and get one of these going. So a new workbook. Get rid of this. What's the first thing we need to know? We need to know what our module VOC is. So what is our module voltage open circuit? Then we're going to need to know what the temperature coefficient is at VOC. So make this, we look over here. Our module open circuit voltage is 48.4. And let me insert a column here, insert a row here. Let's call this max number strings in series. We'll call this safety, if you will. 48.4, that's volts DC. Temperature coefficient of VOC. What are we talking about with temperature coefficient? Well, I really like the LG cut sheet because they provide you some very informative graphs. Here's a chart that looks at short circuit current, ISC, open circuit voltage, VOC, and power, maximum power, all in percentages of nominal. So we know that STC, what this chart is referring to, is at 25 degrees C because all of these lines intersect at 25 and 100. So that means at 25 degrees C, you're getting 100% of your maximum power, 100% of your VOC, and 100% of your ISC. Now what's happening here? Let's look at the slopes. So we're going to focus on VOC because that's our first calculation here. The VOC line is this gray line with a negative slope. So the negative slope is telling us that as the temperature goes up, voltage is going down. Conversely, as the temperature goes down, voltage goes up. So if you're concerned with exceeding a maximum voltage, you want to know in what condition are we most likely to have a maximum voltage issue that we would need to be worried about. Well, as we saw from that chart, that voltage goes up when temperature goes down. We need to watch out for really cold days, particularly in the morning before everything's connected. So the voltage condition is the open circuit condition. So say middle of the winter, where we are, December, January, February, first thing in the morning, the sun's just come over the horizon. Everything is as cold as possible. How cold could that be? And in that pre-wake up condition, how much voltage potential is going to be in the wires of those strings? Well, if we look at our chart, we can see that as temperature goes down, voltage is going up. So that's a bit of an issue. But just how much? Well, they give it to us right here, temperature characteristics. So temperature coefficient of VOC is negative 003. Negative 003 is a percent. So we'll leave that as that. And we're going to need a few more decimal places. All right. Negative 0.3%. Now, what's important to understand here is that is in percent per degree C. We're not really concerned with percentages, though. We want to know absolute voltages. So not only do we have temp coefficient VOC in percent per degree C, but we want temp coefficient in volts per degree C. So how do we get that? Well, that is really as simple as multiplying our VOC times that percentage. What did I forget here? The negative sign. So let's put the negative sign back in. So now we know the temperature coefficient of VOC in absolute volts is negative 0.1452 volts. What else do we need to know? Well, under what conditions is that? That's under STC. So standard test conditions is 25 degrees C. When are we going to have an issue? Well, we're going to have an issue at the coldest possible temperature, or minimum temp. So min temp. Well, how do we figure out what the min temp is? You could do it in a number of ways. You could kind of just Google around, but one of the industry standards is to go to the Solar ABC's website, just solarabcs.org. You don't have to put in the rest. Brings you up to this website with the ASHRAE temperatures. So you put in your location, State College, PA, and you notice on this map, there's no flags or pins or anything. Well, that's going to be a little bit of an issue for us because they don't have data for State College. What can we do? Well, we can go to any number of meteorological websites and get historical temperature data, or for speed, we can just look at nearest neighbors. So if we look at Altoona and we look at the extreme min, because that's the coldest temperature we're going to experience, is negative 19 degrees C. Let's look at Williamsport, negative 19, negative 22, and negative 25. Let's do one more, negative 20. So we're around negative 19 here and here, Williamsport and Altoona. That's kind of right in between State College, or State College is right in between those, and it is in roughly the same mountain range. And I did do a little historical research, and State College is actually ever so slightly warmer. But for the purposes of this exercise, let's go with negative 19 degrees. So we get this out of here. Minimum temperature, negative 19 degrees C. So now we need to know how far away we are from the standard test conditions in order to correct our calculation back to the temperature coefficients that are provided, or to use the temperature coefficients that are provided to correct to the conditions that the system's going to experience. So that's going to be a temperature change. So let's call it delta T. And we need to know the change in temperatures from this equals negative 19 corrected back to standard test conditions, 25 degrees C. So that is negative 44 degrees C. Then what we want to know is figure out, well, how many volts is that? So that's going to be the change, delta VOC, is simply going to be the number of degrees change times the temperature coefficient in volts per degree C, 6.388 volts. Well, let's do a little bit of a gut check on that. So as the temperature is going down, is our voltage going up or down? Well, we know based on this chart that as the temperature goes down, our volts should be going up. So this looks to be checking out that we didn't forget any signs here. We didn't mess up a negative or a positive. So as the temperature is going down, the voltage is going up. So our voltage change is 6.3888 volts when we're at negative 19 degrees C. Well, then how is that going to shape out around the rest of our equipment? So let's look at max VOC. Well, that's going to equal our VOC times the change, or our VOC, excuse me, plus the delta VOC. That means that panel is going to be at 54.788 volts. When it's really cold out. So now how do we figure out how this applies to our inverter? Well, the max volts inverter is 1000. We look back here, absolute maximum input voltage, 1000 volts DC. Okay. So this is how we're going to figure out how many modules we can fit in series. And it's as simple as taking max mods in series. It's as simple as taking our maximum voltage equals maximum voltage divided by the volts we encounter in the worst case scenario. That's 18.2519 modules. You could either just use Excel to hide the decimal points, or you can't have fractional modules. So there's no way to have 18.25 modules in series. You either have to have 18 modules or 19 modules in series. And if you wanted to continue using these calculations later, one way that you can make this even more useful is to just throw in the round down formula of our number times, or at 0 digits. That means max number of strings in series or modules. How come nobody called me out on that? Max number of modules in series for the string is 18. Well, let's use this tool to figure out max modules in series for operating voltage range. We know that that is 950. Easy as that. All right. So next, we're going to get to looking at inverter calculators that are supplied by inverter manufacturers, and they're extremely useful tools. But I think it's really important to at least understand the background and the basics of where these calculations come from. Because if you don't grasp the basic concepts, then first of all, there's no way for you to check against what the inverter software is saying. Yeah, you can probably trust it, but if you are a stamping engineer, then it's kind of on you at the end of the day anyway. But it's also important because as we go through the iterative process, we're going to need to shift some panels around on the roof from one roof to the other in order to get our strings to all be round numbers of modules, preferably all the exact same number of modules in series for every string in the array. And we're going to see that maybe it's 15, 16, 17, 18, 19 modules. And if we don't know really the realm of the reason for these calculations, we don't have any basis for any future decisions. But now that we're looking at kind of what goes into these calculations that are in the background of the calculators, then it allows you to be able to make informed decisions as you continue to move forward. So let's start looking at how Selectria would size this. So if we go over here, click here to use the string sizing tool. It's just selectria.com, and you click through for the string sizing tool. You can just input this directly, but we'll click here, and I'll zoom in a little bit. Let's throw in our information. So we know we're using LG modules, and the module we're using is right here, the LG 365 N2W B3. There we go. Our low temperature is -19°C, and our high temperature is, let's do 31°C is our 2% average. Pretty big window, State College. All right, mounting method is less than 10 degrees, greater than 10 degrees. Oddly enough, we are exactly at 10 degrees. If you wanted to be really sure, you could try both. The flatter the modules, it's going to have an increased temperature coefficient on the calculations because there's less convective cooling under the modules. So you could try both, but I think we're probably going to find out that not too much changes. So array STC power range. How do we figure that out? Let's just look at one roof. So if we hide everything except for modules, let's get rid of the shade just for convenience sake. Let's just look at this one roof here. 159. Bring the calculator back up if I've got it. I don't think I do. Easy as this. We go 159 times, we're using 365 watt modules, 58 kW, or 58,000 watts. So let's bring the sizing tool back up. And where does 58 fit? 58 fits right here, between 50 and 70. What inverters are we using? Well, we are using the 28TL. It has one of two MPPTs, or you can use standard, which is both MPPTs. We're going to pick that one. And it's telling us it defaults back to 25 to 30, but you can then bump this back up to 50 to 70, and then it's going to select multiple inverters. So yes, I've read the terms and conditions. And before I click show results, I want to look at these numbers up here and see how they're comparing to our calculation. Because they provide STC wattage, 365, sounds good. Current maximum power, voltage maximum power at 25°C, voltage maximum power, temp coefficient, the warmest day temp, coldest day VOC, and VOC temp coefficient, and the VOC at STC. So let's see if those numbers jive with our math. So module VOC, 48.4, 48.4, perfect. Temperature coefficient VOC. Now that's not percent per degree C, that is absolute volts per degree C. They have 0.1355. We have 0.1452. Now what's going on here, you may ask? Who's wrong? Who's right? Kind of interesting. I think we're both right. So if you look here, our VOC we used was -0.30. However, that's based on this spec sheet that I downloaded, I don't know how many years ago, months ago, whatever. And they get their information from what's called the Photon database, which is a published database server that companies can use the API to pull information down. And the Photon database has these modules in at negative 0.28 VOC. So let's see what happens if we put that in. Negative 0.28. Oh. Negative, come on, Excel. 0.028. 0.1355 to 0.1355. Beautiful. So here we can see that all the math appears to be shaking out. Theirs is a little different than ours because we use the cut sheet. And I'm going to go back to that and just see if that has any implications over the full calculation. But for now, let's do show results. And here we go. After you click show results, it's going to give you this chart right here that covers power at STC in watts DC. This is another rating, PTC, and then they've got power, so AC power, total number of modules, number of strings, number of modules per string, and a couple other conditions. Now, what we're doing here is we're checking our math for modules in series, so the number of mods per string. Let's see how their math looks. 16, 17, 16, 17. Oh, they have an 18 here, and then they've got some really low modules. That's not going to be a good choice. Here's an 18 as well. They don't have any 19s, but they have an 18. Now what's happening here is they're looking at putting strings together that are all matched. Those matched strings then start to be multiplied times the number of modules per string times the number of strings. So we can see that this is suggesting there's 2 inverters and there's 12 total strings. So that means you've got 6 strings per inverter. And if we look at our inverters, we can look at some more information on them. We've got maximum operating input current. That's how many amps can go per string. And then how many maximum power point trackers. So how many controllers effectively are in the inverter. So it says there's 2 MPPTs, so maximum power point trackers, with 4 fused inputs per tracker. So that means 2 times 4 is 8. So that means 8 strings per inverter. So that means you could have a theoretical maximum of 16 strings on this inverter. And they do show that here. So 16 strings with 12 modules per string. But we know we want to keep our number of strings as high as possible in order to mitigate voltage drop. So I'm interested in the 18 module strings. And this one's looking pretty good. So 18 modules with 9 strings. I would rather higher voltage, lower current any day of the week in order to minimize voltage drop and keep the system as efficient as possible. However, what it's saying is you may run into a voltage issue when it's cold. So voltage maximum power during cold is 18 times 45.56 gives you 821 volts. Well, maximum power input voltage range is 800. So what's going to happen there is you're exceeding the limits of the inverter, and it's going to go into some kind of self-protective state, meaning it's going to have to curtail. You're going to be throwing power away. Well, I would rather throw power away on the coldest days of the year as opposed to the hottest days of the year. So these are VMP hot day issues, meaning on a hot day, your voltage is going to be too low. So as you look at here, you've got a lot of those issues where your VMP on the hot day is going to be below your VMP range. So possible derating due to low string voltage, 446. Well, what's our maximum power input range? The low end of that is 500. So 446, I was here. That's less than 500, meaning your inverter is not going to be able to maintain its highest levels of efficiency. So where would we go from here? Well, now that we kind of understand where these calculations are coming from, because we've performed at least one of them ourselves, this can inform our decision of where we want to go as far as inverter selection. Now, we know based on the calculator math that we want to have 58 kW input. So let's take a look now and see how that's going to coordinate with our array. So bring the array back up. We know we have 159 modules. Well, 159 divided by 18 is 8.83, not a whole number of modules. Let's do 18 modules. Let's look at it from the other direction. Times 8 strings is 144. 18 modules times 9 strings is 162. So we either need to get to 162 modules, so we would need to add 3, or we would do 18 times 8, 144. We're at 159. We would need to delete 15 modules. Well, I'd really rather not delete 15 modules. Let's just look at 17. So 159 divided by 17. Okay, 9.3. So 17 times 9 is 153. 17 times 10 is 170, obviously. 170 minus 159 is 11. So we would need to add 11. There's no way we're going to sneak 11 modules in here. Or we need to subtract 6. I'd really rather not subtract 6 if we don't have to. So I'm starting to lean back towards 18 module strings times 9 strings. That's 162. We got to get to 162. We're at 159. We need to add 3 modules. Can we fit 3 modules in here? Well, let's bring everything back up. We could maybe squeeze in 1, 2, 3 here. That looks realistic, though one of the things we didn't consider is access path to this equipment. So you can see here, there's no way to get to this equipment without stepping over or around modules. That's really less than ideal. So I'm actually going to delete a module, at least one, so that somebody getting onto this roof can access this equipment without having to step over modules. So now that gets us 158 modules here. So now we need to add 4. That's not sounding very good. So what was 18 times 8? 144. We're at 158. We could put modules back in there, I think. That's probably pretty safe. So let's copy these 2. Put you guys right there. So now we've got those back in. Those are probably going to see the shade. I think if we went to December 21st and we start looking, yeah, those are going to be pretty heavily shaded in the morning. So less than ideal, but it's probably pretty good to get more modules on this roof. We can do the math later and see how that looks. But that's one way to go about this exercise. or my calculator's still here. Now, what does 17 modules look like? So 17 times 8 is 136. 17 times 9 is 153. So 153 from 60 is 7 modules. So we'd have to delete 7 modules. 10 strings of 16 is 160. That's kind of a perfect fit. Our voltage is a little low at 16 strings per module, but it's such a perfect fit on this roof that we're going to go with 10 strings of 16 at 160 modules and see how that runs. So let's go to our drawings and say this is going to be inverter 1, typical 10 strings of 16 modules. So that's 16. String 1, string 2, that's 16. This is 16. And this is going to go to string 10. And that's inverter 1. And this is going to be building C. We'll see how this shakes out as we move forward. We may need to have we may need to add another row here because we may have 3 different configurations. But for now, this is where we're at. Typical 4, 10. All right, let's look at the other buildings. So this is building C. I know that naming convention, so it's A, B, and C. It's not left or right, but that's neither here nor there. So let's go in the middle. Let's look at building B. 131 modules. Can we bring this over there? Shrink it. Let's see how that stacks up. 8 strings of 17 is 136. Could we sneak in another 5 modules? 1, 2, 3 right here, maybe. Once again, we don't have access paths. So let's at least throw in an access path there and an access path there. That gets us to 129. Does 129 fit on this chart anywhere? Looking. 129 is actually a little bit low. So what we're going to do there is we're going to switch to another inverter. So we're going to switch to the 23. Let's see how that works. So 23 TL. I have read, and we know that this is 129. Bring the calculator back up. 129 times 365. We want to be in the 47 range. So 42 to 50. Show results. Okay. We've got 129, and they've got options at 128. 8 strings of 16. Looks like this building is going to fit with 16 modules per string. Conventional wisdom for me would have been a little bit higher because we want to keep the voltage up, but based on the constraints of this building, it looks like we're running with 16 module strings. It's pretty easy to delete one more module. Typically, we'd like to add modules, but we'd have to get to 36 or 35. That's just not going to happen. Our option is to delete. So let's delete one more module. Anything getting bad shade in the morning? 9. That one's pretty bad. 10, 11, 12, 1, 2, 3. Access wise, pretty easy access around. Let's just get rid of one of these around equipment. Later on, as people are installing this in the field, they may have a much more obvious choice which module they want to get rid of or where they want to shift them. But at least now we know we can fit 128 modules with 8 strings of 16. So let's throw that in here. Add some text. 16, 16, 16. This is going to be inverter B. That's pretty obvious. We probably should have just named this one inverter C. We can fix that later. Can we edit? Yeah, we can. Inverter C. Slightly less than ideal, but you get the idea. Typical for 8. I'm doing this in PDF form. Obviously, you'd want to do this in your CAD software. So this is string B1, B2, B8. That's inverter B. Building C's inverter C. Let's finish it up. Whilst we're here, last building, building A. 178 modules. Well, let's do the math again. 178 times 365 is 64.97. So basically 65 kW. That's probably going to be the next inverter up. We should probably make a note here that this inverter is a PVI 28, but this inverter is a PVI 23 TL at 23 kW. Beautiful. Where are we at? 176. I'll be darned. 16. Everything is rounding to 16 nicely. Now, clearly you could see that we could have done this pen and paper, done the math with multiplication, but this chart makes it really easy to just look at the chart, and then you could have created an Excel-based chart based on the number of modules in series, and then multiply the number of strings times the number of modules, created the matrix. But the tools exist. Why wouldn't you use them? And as long as you can gut check them and make sure they're making sense, then I see no reason not to use the tool. And as you can see, as we're working through this, I mean, it's really easy to just flip through the matrix they've calculated and see how it fits with your design. So if we go back to our design, we've got 178 on this roof. It's pretty darn close to 176. I think that's kind of a no-brainer. We've got no warning issues. The cold voltage is going to be great. hot voltage, you're within the window. The DC to AC ratio is a little low here. Typically, you'd want more inverter or more panels to your inverters, because if you don't have more panels to your inverters, you could theoretically be overspending on inverter. And because of that, let's see what the next inverter up is. Oh, what do you know? We were still on the small one. Let's go to 28. Run the calculation. Yes, I've agreed. Oh, they keep defaulting you. 50 to 70. There we go. 10 strings of 17. It's 170. 176. 11 strings of 16 with 2 PVI. 28 TLs. Okay. Looks like we're going with strings of 16, because all we have to do then is delete 2 modules. Well, let's look at the ones that are going to perform the worst in the shade. 9 a.m. Not a whole lot of shading issues. 1, 2, 3 p.m. Okay, these are pretty close to this equipment, so let's get rid of this module and this module. That brings us to 176, 176. So if we bring up our drawing, and then, ooh, it's, it's getting real messed up. I'm not going to correct that online with everybody. I'll probably clean this up for the next video as we get to looking at the construction drawings. It would be, well, frankly, really boring for me to sit here and clean this up in PDF format. That's just unrealistic. So clearly that got a little painful towards the end there. In the next one, we'll walk through cleaning that up, making a nice clean set of drawings that accurately represents the electrical system as we currently have it designed. Look forward to seeing you there. Thanks. Bye.